Bismillahirrahmanirrahim. Assalamu alaikum. Let's continue our discussion on regression. In the previous video, we talked about setting up a regression problem. We also introduced linear regression. We formulated it as an optimization problem, and we employed vector calculus to find analytical solution for a linear regression problem. In this video, we will focus on polynomial regression, and we will revisit the concept of underfitting and overfitting. Why do we need polynomial regression? If the relationship between the inputs and output is not linear, so we don't have a straight line, we have this such a non-linear relationship. To model such a non-linear relationship, we can use polynomial to model this. Uh, in this video, we will formulate the polynomial regression problem for a single feature, single variable regression. We will also see very shortly why do we refer to this polynomial regression as linear in parameter regression. In fact, we will formulate the polynomial regression problem as a linear in parameter regression problem, and this will help us in using the solution we developed for linear regression problem. And in this video, we will also revisit the concept of overfitting. We will talk about a couple of solutions which we can employ and to avoid overfitting in regression. Let's start with the formulation of a polynomial regression. So we take single feature, single variable regression. So our D is 1, input is scalar. And we want to model the relationship between input and output using a polynomial. So our model would be given by mth degree polynomial. So here, so theta naught is again an offset. We have theta 1, theta 2, and theta m. So we have these m plus 1 number of parameters, which I have indexed in the form of a vector theta. So our model depends on this theta, right? So model is capturing structure. Structure is polynomial, and number of parameters, we have m plus 1. So m is the hyperparameter of the model, because when you change m, you get a different polynomial. So we say m is the degree of polynomial, which is characterized by, and model is characterized by m plus 1 coefficients. So theta naught, theta 1 to theta m. So these are the coefficients which characterize our model. So as I said, m is the hyperparameter of the model, and it determines the complexity of the model. Obviously, when you take m is equal to 1, you only get theta naught plus theta 1x, which is indeed a linear regression problem. We can use linear regression to find these coefficients by formulating the input x and its powers using a vector valued function. What do we mean by this? So what do we have here? Theta naught, theta 1, theta 2, theta m. If you see, the unknowns, they are still linear, right? So we're not raising, so for these unknowns, so we don't have any powers associated with these theta naught, theta 1, theta m, the parameter of the model. Right? So we only have powers with the input variable, right? We have input to the power 0, and to the power 1, 2, and so on and so forth, up to power m. If I split my parameters, if I somehow define, if I somehow reformulate my inputs such that I can split my parameters and inputs, I can formulate, I can represent my model as a linear model, or what we call linear in parameter. To do this, I'm going to define this function g of x. It's a vector valued function that takes input x, which is a scalar, and it gives you a vector. So it's a mapping from R to R capital M plus 1. Right? And this is given by So you get the first one, and you have x, x squared, x cubed, x4, and so on and so forth, x to the x raised to the power m. Right? So it's a vector valued function. If I use this formulation g of x, right, I can reformulate my model. So I can reformulate my model as this. So if you use g of x as 1 x x squared and theta as theta naught, theta 1, theta 2. So you take in the product of these two, you can easily see that this is in fact equal to polynomial, right? So I is equal to 1 to m theta I x to the power I, x to the power I. This is indeed a polynomial model. But if you observe this, so this model is linear in terms of parameters. And due to this, we refer to polynomial regression as a linear in parameter regression. So here I have chosen g of x as 1, x, x squared, and xm. In fact, this g of x can be any function of x, right? So we can generalize polynomial regression, and we can have g of x as any function of x. It does not need to be polynomial. For polynomial regression, it is polynomial, but in general, we can have g of x as any function of x. For example, we can have this g of x, right? In which the first is 1 over x sine 2 pi x, x squared, exponent of x. We can have any formulation, we can have any relationship between x and g of x. Right? Okay, if I use this g of x, my model is still linear in parameter, right? Because theta 0 would be associated with 1 over x, theta 1 would be associated with sine 2 pi x, and so on and so forth. So you can see here that we are studying a broad class of regression problems, right? Okay, so what's happening? So I have taken, so the relationship between input and, for example, it is 1 x x squared. I have taken these polynomial or these relationships out of model, and I have defined a vector valued function. So this is kind of feature engineering, right? So I have an input that goes through g of x, and g of x goes to the model, right? Okay. So for this formulation of the model, I can again define the residual error, and we will define the loss function. Right? So for n data points, right, so we have n different data points x, y. We can define the residual error e1, e2, en. So e1 is the error for the first input output, e2 is for second input output, and so on and so forth. How did we define error? Observed output minus the model output, right? That's how we define a residual error, right? So e1 would be given by y1 minus what is predicted by model, and that is simply g of x1 transpose theta. What is g of x1? 1 x1 x1 square, so on and so forth, x1 to the power m. This is for y1. So e1 is equal to y1 minus, this is my g of x1, and this is my theta. And if we do for each of the data point, we get e1, e2, en. Right? Again, if I call this vector as y, and this matrix in which we have all the x and its powers, we get capital X. If we denote it with a capital X, and this is my parameter vector, again arrow will be given by y minus x theta, right? We have seen this before. We have seen exactly this formulation. Previously we had w instead of theta, but here we have theta, right? And in fact, we are capable to solve this. So what is the solution? The solution that minimizes the value of theta, that minimizes mean square error, root mean square error, or least square error is x transpose x whole inverse x transpose y. Again, the assumption here is that x transpose x is invertible. So we derived this in the previous video. So that's all. This is the polynomial regression. So polynomial regression is linear in parameter regression, right? We can use the solutions we developed for a linear regression, we can use for polynomial regression. Okay, let's talk about one example of polynomial regression. So in polynomial regression, we need to devise some strategy. How do we choose this m? Because m is hyperparameter. For different m, you get a different model. So in linear regression, we do not have such a variable. Okay. So in linear regression, the number of variables depend on the number of input. But here we have this hyperparameter, and we need to devise a method to choose this m. Before we devise a method to choose m, in fact, we will devise a method with the help of one example. Okay, let's assume that our process has this function that we take f of x equals sine 2 pi x. So this f of x is sine 2 pi x. It's a simple function. And observation would be given by y is equal to f of x plus n. So f of x that goes here, corrupted by some noise. Right? And we assume that the noise is Gaussian. It is some small variations around the function value. And our model is a polynomial, right? Defined by or characterized by the degree capital M. If I visualize this data and we only take n points, this green is my true function process, and these blue are my observations. Right? I have taken 10 observations between 0 and 1, and I have taken uniformly spaced. Right? So, okay, and let's model it for different values of m. So we have f of x sine 2 pi x. Model is a polynomial of degree m. Let's say you attempt to model this with m is equal to 0. When m is equal to 0, you only have a bias offset. When you model it, it would be, what is the best model? In fact, it is sum of all, it is an average of these 10 data points. And the average would be slightly above 0 if you take these blue points. So it's a poor model, right? Because you're only using DC bias to model something nonlinear. Let's model with using a straight line, m is equal to 1. It is capturing some of the variations, right? But again, it's a poor model, right? What about m is equal to 3? Get this. If we keep on increasing m and say you increase m and you take m is equal to 9, what did you expect? So did you expect this red curve to be exactly equal to green curve or something different? When you fit m is equal to 9 model, this is what you get. What's happening here? So why do we get this widely varying model? So when m is equal to 0, we had underfitting. The model is very simple. But when m is equal to 9, in fact, the model is too complex. So we have overfitting. So in fact, model is not very complex, but so there is some issue with the fitting. We will see very shortly that if you still use m is equal to 9, you can have red curve that matches with the green curve when you have a large number of data points. We will see this very shortly. Okay, let's talk about this overfitting. Why do we get overfitting? So model is fitting to the data, not the actual true function. For m is equal to 9, so see, our model is perfectly passing through these blue points. So we have a 0 residual error in fact. Why? Can you make a connection? You can. So when m is equal to 9, how many parameters do we have? 10. How many data points do we have? 10. Right? So that system x transpose x inverse x transpose x transpose, I think that was y. So that system would be giving you exactly the parameters for which your model is passing through these points. But the question here is this a good solution for this problem? No. The model is oscillating, and it is oscillating very wildly and is not close to the true function. This is due to the overfitting. So in this toy example, we had information about the true function, and therefore we can conclude that m is equal to 9 is not a good model to fit the data. So in this toy example, we had information about underlying f of x, but in practice, we don't know f of x. How can we decide whether the model is fitting to the data or the model is in fact capturing the variations of the process? So how to choose model M, or how do we tell when the model is overfitting if we do not have any prior knowledge, if we do not have any information about f of x? So we talked about one solution in the second video. That was you use train validation split. So M here is hyperparameter. When we carry out train and validation split, so we get a poor generalization performance because of overfitting. So when it is overfitting, we expect a poor generalization performance. That is large error on the testing or validation data. The solution is train validation split. How do we employ this solution? If I plot the loss function, say root mean square error versus model degree for training data and for validation data. So I should be expecting curves something like this. If you see the blue curve, that is the loss on training data. And this loss keeps on decreasing as m increases. And when m is equal to 9, the loss becomes 0 because the model is fitting to the data, is exactly fitting the data, but not the true function. And since it is not fitting to the true function, you expect high loss on the validation data. But if you have this red curve, so using this red curve, you can find the optimal order, the best order. So you would say that the best order would be somewhere here, or good choice of m would be somewhere between 3 and 5 and 6, 3, 4, 5, 6. Okay, so this is one solution for model selection, how to choose parameter, how to avoid overfitting, that we split data into training and validation. Okay, let's talk about let's review this overfitting from a different perspective. Okay, let's pose another question. So m is equal to 3-degree polynomial is a special case of m is equal to 9-degree polynomial. Agree? So if you for a 9-degree polynomial, if you make the coefficients theta 4, theta 5 to theta 9 is equal to 0, what you get is a 3-degree polynomial. The question here is, then why m is equal to 9 gives us poor performance? And to answer this, we look at the value of the coefficients we get when we solve polynomial regression problem for different values of m. Right? So we talked about m is equal to 0, 1, 3, and 9. Right? And if you find coefficients for these values of m, we get these coefficients. If you see, the magnitude of coefficients is increasing with m. If you make, if you only keep these 4 coefficients for m is equal to 9 solution, and you make the rest equal to 0, you cannot recover m is equal to 3 solution. Because for m is equal to 9, the 10 coefficients are exactly tuned or rightly tuned for 10 data points. Right? So we have same number of data points, and we have same number of data points is equal to the number of coefficients. And therefore, we're getting poor performance when m is equal to 9. So how to avoid overfitting? We talk about one solution, that is separating data into training and validation. Right? So for that solution to work, what do we need? We need more points, right? The polynomial degree is the hyperparameter of our model. It's like we had k in kn, and this is controlling the complexity of the model. If you use separating data into training and validation, and you say stick to m is equal to 3, this is kind of restricting the number of parameters to model your process, right? So we encountered overfitting for m is equal to 9 because we did not have sufficient data. And the solution 2, which is language solution 1, that do not restrict your polynomial degree, right? But instead take more data points to avoid overfitting. For example, we had this very, very poor solution when we took 10 data points and we had 10 coefficients. But if we keep the number of coefficients same, we keep m is equal to 9 and we take more points. Say you take n is equal to 15, so you get a relatively better performance. But when you further increase number of points, say you take 100 data points, so the 9th degree polynomial degree is same. 9th degree polynomial is very, very close to the true function. Why? Because the number of coefficients is much smaller than the number of data points you have. So the coefficients are not fitting to the data. Right? We have talked about two solutions for overfitting, and these are linked. So the first one, you split data into training and validation. And second is you take more number of points. But in practice, getting more data is expensive. What else we can do to avoid overfitting? And third solution to avoid overfitting is regularization. And we will talk about this in the next video. So we will, so regularization itself is a very broad topic, and we will start with the general formulation of regression, and then we will take this polynomial regression as a special case for regularization. Okay, so in this video, we have talked about polynomial regression. We formulated polynomial regression as linear in parameter regression, and due to which we could use the solution we developed for linear regression. And we also revisited the concept of overfitting, and we talked about two solutions to handle overfitting. Okay, we stop here and we'll continue in the next video. Allah Hafiz.